Okay, so we were looking at probabilistic model checking. I mean, we started with uh, Markov chains. So essentially, what is the Markov behavior? Like the next state essentially depends on the current state and doesn't depend on the history, right? And that is the Markov property. And these probabilistic behaviors, I mean, this is quite relevant. I mean, we find them in several systems around us, like if there is a message loss and so on with certain probability. And how do we define Markov chain? It's like a transition system, but now you have some probability distribution from a state to its set of successors. Okay, there's a probability distribution, right? And essentially, like we saw some examples. In particular, like we also saw this Chapman-Kolmogorov equations, where you have like the probability to reach from some state S to S prime in n steps is equal to like you see what is the probability of reaching some state S to S double prime in m steps, and then from S double prime to S in n minus m steps, and you sum it over all these intermediate states, the probability reach there. Okay, and then if you are particularly talking about starting from an initial state, then you can simply take the nth power of this transition matrix and then multiply it with the initial distribution, right? This is the thing. And then we were also talking about like this Knuth's die. You can model this like a die with a coin toss, like coin which will have probability half of seeing a head and half of seeing a tail. You can essentially do this. But then one would also like to check that this model is correct. So essentially what we would like to do is that the probability of reaching these states should be one. I'm sorry, 1/6. Okay, yeah. Right. Uh, um, right. And we also saw some example of a simple communication protocol. And we said, like, for example, this is an example of a strongly connected component. In fact, this is an example of a bottom strongly connected component. So what is a bottom strongly connected component? Like a strongly connected component from which there is no leak out outside that component, right? There is no probability leak that is going to happen outside that set of code. Now, and there may be some paths, like if you say that I will always be in this path, always be visiting this path, right? I come here and then I'm always restricted to this. That has essentially a probability of zero. So that infinite path has a probability of zero, measured zero. So in fact, if you see this strongly connected component, there is no probability which is leaking outside, right? In fact, this is the whole Markov chain. So with probability one, we can see that every state will be visited infinitely often with probability one. Okay, the set of states which are visited with probability visited infinitely often with probability one, that is in fact this entire BSCC, bottom strongly connected component. Okay, uh, with probability one, all the states of the BSCC are visited infinitely often, right? Okay. So then we also talked about how do you compute the events in a Markov chain, right? So the outcomes, like, so if you talk about the probability space, like if you talk about a sigma algebra, right? So in sigma algebra, you have these outcomes, and then you have some subsets of that of those outcomes, right? And then in a probability space, you also have a notion of a probability on these events, right? So you should, so this there in the book or anywhere, I mean, this you should, if I mean, it's all like we intuitively understand, but I think it's also good to sort of go back and see these definitions formally if you haven't seen them for a while. But the thing is like here the outcomes are all the infinite paths in the Markov chain, and the events are subsets of these sets of paths, right? And when you talk about the sigma algebra, so there are also some like, so it's usually uh, like if you talk about the events, so they should be closed under certain operations, like it's closed under complement, countable unions, and so on, which also gives that it's closed under countable intersections, right? Because intersection can be. So if you talk about, let's say, some countable intersection of these some xi's, right? So this I can talk about. So if it is closed under complement and union, so then this is like union of xi bar, then this, right? So essentially, if you talk about it's closed under complement as well as countable union, you also get over countable intersection. Okay. So uh, right? And now we defined these cylinder sets, and we talked about like these events are essentially like the measure is obtained using the cylinder sets, right? So the cylinder sets were this infinite extension of finite paths, right? And so, for example, if I talk about there is a target set T and probability of the event eventually T. So these are, we can consider all the, for this, we can consider all the cylinders such that in m minus 1 steps you are not reaching T, but on the mth step you are reaching T. And you consider the union of all such cylinders, right? So in fact, so this is just one example, but you can also talk about other kind of events. For example, so the set of events here, it consists of all the cylinder sets. Okay, so and for where pi hat is in fact this finite path, and this pi hat ranges over like it's over all the finite paths. And then I was talking about like this ft, right? And this is something we saw how you get the measure of ft. But then you can also try to see like how you can do how you can prove essentially these events are also measurable. Okay. So for example, like all these events are measurable. So we did not discuss. So we just looked at this one example, but you can try to figure out like that eventually globally T, globally eventually T, globally T. So all these events are in fact measurable, right? So how do you do that? Like essentially you will try to have to express them using the cylinder set, right? So you can talk about, suppose, let's say union, countable union of some thing is, of some cylinder sets is measurable, and countable union of this countable intersection of the measurable sets, that is also measurable. And then you can talk about maybe sometimes like union of intersection or intersection of union and so on, right? So you can think about such things, like how you express these events in terms of like countable unions or using these operators, essentially countable unions, complements, and countable intersection of the cylinder sets. Clear? Right. So this is something that we saw, the FT, okay, which is just to take the countable union of such cylinder sets, such cylinders, right? And that's um, yeah, and like, so these cylinders are all pairwise disjoint, so you can just sum them up. Yeah. Okay. Good. And so as an example, we talked about like probability of eventually T, and we looked at all the different the cylinders corresponding to, right? Yeah. Hmm. Right. Yeah. So we looked at all these different cylinders corresponding to eventuality, which are like in some n steps you are reaching t, and n minus one steps are you are still not in sorry, you are reaching two, and up to n minus one steps you are still not at two, right? And you can talk about prefixes of essentially different length, prefixes of length 3, 5, 7, and so on. And you can sum them up. And if you do that, you get these GP series, and we can indeed compute this, and the probability is 1 over 6. Okay, and then we also saw that there are other ways to compute these probabilities by setting up some linear equations, right? So these are also called sometimes linear recurrences, and like you have, let's say, a variable xs which says that it denotes what is the probability of reaching capital T from that state S. So if xs is equal to 0, if t cannot be, sorry, if t cannot be reached from S, right? I mean, the probability is 0. If you are already in T, then you know it's 1. Okay. Now, we also know that for the other states, it can be like between 0 and 1. Even sometimes it's not necessary that, like, suppose there can be a state which is outside T, but from which T can be reachable. For that also, xs can be xs for state S, the xs, the value can be equal to 1. 1. It's possible, isn't it? Like, even if it is not in T, but you know that, like, the probability of reaching there is actually 1. With probability 1, you are going to reach there. So there may be some states which are uh, outside T, but still xs is 1. So this is not an if and only if. So it is just like if s is if belongs to T, then xs is 1. But it can be possible that there are some states which are outside T for which also xs is 1. So when we are setting up the linear equations, so we set up the linear equations with some variables corresponding to these what we called as S question, right? Like which was S minus S equal to 0 union S equal to or maybe some, yeah, S equal to 0 union some T, where T may be a subset of S equal to 1. Okay. So this is fine. I mean, I can do this, and I will eventually figure out that that excess for that particular state is in fact 1. Okay. Even if I don't initially get to understand. So, I mean, there may be different ways of initializing this, but something which will be efficient, which will make the matrix smaller. So if you start with fewer states, then of course things will be faster if you have to compute it, right? Because you are doing all these matrix vector multiplication, etc. So this will be faster if you start with a small set of small S question. Clear? But it's not unique that how you are going to define the S question. It's not necessarily unique. That's all I'm trying to say. Okay. And this is how you can say that xs is summation of PSS prime times xs prime plus the probability of like S to S prime, S double prime, that is like you are reaching T in one step. And this is like reaching T via S prime, where S prime is in this S question, right? So we set up the linear recurrences like this. And then we solved like for this nodes die just to check what is the probability, for example, um, indeed like that eventually from S0, right? So we computed x of S0 for the property that you want to reach 2, eventually 2. And this we could compute that this was indeed 1 over 6, right? So you could verify that whatever we are talking, whatever intuitively we understand, that is indeed correct. And then we talked about something which is a slightly more general kind of reachability, which is a constraint reachability. So this is like you were talking about C until T, for example. Okay. So C until T, where it's more or less like you can talk about phi 1 until phi 2, where C is the set of phi 1 and T is set of phi 2, like this. Okay. So now, uh, uh, so for example, I think we were looking at such a, such a formula. It's not the case that there exists a path of C on T. Okay, and uh, so, okay, so if you have, let's say, sorry, so if you have such a formula, then if you, in fact, if you don't have such a path from some set of states, so they are going to satisfy this C until T with probability 0, right? So what we are trying to do, we are trying to say, what is the probability of satisfying this formula, like probability of satisfying this path formula C until T. So, right, from a given state, what is the probability of satisfying C until T? Now, if from a state there doesn't exist any path which satisfies C until T, then that state is going to satisfy this formula C until T with probability 0, because there doesn't exist any path, right? So this is what it says. Like, so, and then, uh, for example, if I, so I'm defining the S equal to 0 and the S equal to 1 here. So S equal to 1 is like the set of states which satisfy C until T with probability 1, just by definition, right? And so I, as I was saying, that my T doesn't necessarily, it has have to be unique. Like T is a subset of this S equal to 1, I can start with. Okay. So I can have this as question as the set of states which are neither in S equal to 0 or S equal to 1. Or I can even talk about like a question which is like S minus S equal to 0 is equal to, and T instead of S equal to 1. I can even start with a subset which is like, which is a subset of S equal to 0. Right? But smaller the my S question is, the faster will be the evaluation. Okay, so that's the thing. And this also you can solve using this sort of like a linear recurrence, x equal to ax plus b, where what is your A? A is the transition matrix, x is like the set of, it's those vectors corresponding to the set of states in that S question, and b is essentially like in one step you are going to reach the set of states which satisfy probability 1, right? So S2 is equal to 1. So these are the set of states which satisfy with probability 1, and you are going to do this in one step, right? So if you, and we possibly saw this example, right? You have essentially like, so what was this example? What were we trying to see? So the probability of not C until D, right? So can you say how did we solve this? Like, so we see saw S0, right? So not C until D. What is this S0? We had S3 and S4. They are in S equal to 0, right? And S equal to 1, we have already this, right? So now the that question are these two states, S0 and S1, right? These are the S question, and then we set up the this sort of a linear recurrence, right? So x s0 is essentially half of xs1, and xs1 is 1 by 3 xs0 plus 1 by 3. Okay, you can solve it and you can get xs0 is 1 by 5. So that means the probability of satisfying this particular formula, this particular path formula, starting from S0, this was 1 over 5, right? So this is what we computed. Right. Um, okay. So I think now what I was saying, I think this was towards the end of the last class, that in fact, like we are going to use these operators for PCTL. Okay. So yes. Okay. So yeah. So it was just a recollection of what we were doing in the last class. And when you talk about, for example, constraint reachability, like you can also talk about other kinds of events, derived events. So, for example, eventuality is the same as the set of states until t, true until t, right? True is satisfied by all states. Globality, it's like it's not the case. We have seen all this, like it's not the case that eventually you get to see something which is not in t, right? Then probability of globality is 1 minus eventually something outside, right? So you can actually, sorry. So this is 1 minus, I should say, probability of this, right? Of this event, correct? Okay. Uh, right. Okay. So, in fact, like you see that now we are sort of like talking about some formulas here, and we will look at this logic called PCTL, like probabilistic computational tree logic. We'll see how is it's kind of related to CTL and how it is different from CTL. Good. And there is also, as I was saying, that sometimes you can also talk about, like you start with the valuation, you don't know the value of a certain event in the beginning. So you say that suppose the value is 0 to start with for all the states, at least for the ones that you are trying to compute in the S question, you start with a 0, and then you multiply with these transition probabilities, and you do it iteratively, and eventually it will become like you will reach that particular value, or you will reach actually maybe something very close to that value. And you will stop your iteration when you say that the values don't change by more than an epsilon, right? So let's say like here I'm going to talk about such an operator gamma. So you have the S question, and then this is like the values between 0 and 1. So you have such a vector, right? And the gamma essentially transforms from one vector to another vector. Like you start with some initial value, you get a new value. Again, on the new value, you apply the gamma operator, you get another new vector, and so on, right? And it's just an iterative computation. And the idea of the gamma, the way you are computing, is essentially again this gamma y equal to a y plus b, where a is that transition matrix. Okay. So you start with x0, which is in the beginning. I'll say that 0 is the vector consisting of only zeros. And then xn plus 1 is gamma times this, that xn. This is, I mean, this is a function. You are applying gamma on this vector, right? And you are computing, you are defining this as ay plus b. Okay, so you are applying this gamma function. And so if I do this, now, after this nth iteration, so I have this xn after this nth iteration. Now, suppose if I start with initially, like I talk about, let's say, something like that my S1 is the set of states which have like, or if I start with this T, which are essentially the set of states which satisfy this T directly. Okay, so satisfy the T directly. So this I sort of like I have those set of states, and then here this says that I am reaching uh, from S to this set T, but while seeing only C. Okay, while seeing only C. Now, what I'm asking is this, Like when I have this x of n, what does it denote? Like, uh, so again, uh, so I'm trying to compute this thing, let's say. So S satisfies, what is the probability of S satisfying C until T? Okay. And now if I'm doing that, taking the nth power, right? Not nth power, sorry. Like I'm applying the gamma n times, right? So, uh, so, so I claim that I'm going to get this C until less than equal to NT, less than equal to NT. Okay. Rather than saying that exactly N. Okay. So what does it mean? That what is the probability that I'm going to reach this T uh, within at most n steps. Okay, I'm doing the multiplication by, so let's just simplify it. Maybe our C is just that S. So it's like true until less than n T. Okay, eventually in less than n. So all I'm trying to say is that my xn, I am claiming, how am I getting the xn? I start with the x0, which is the zero vector. I'm applying the gamma n times, right? I'm applying the gamma on that vector n times. So x, then I apply gamma, I get x1, then I apply gamma, I get x2, x3, and so on. Now, what I claim is that this gives me the probability to reach t in at most n steps and not like in exactly n steps. Why is it true? Or why do you think this should be the case? Is the question clear? Right? So, why do you think this is the case? That I'm saying that it is not in exactly n steps, but you are reaching the t in at most n steps. Why is it the case that you are reaching there in at most n steps? So what is my x1?
X1 is the probability you reach in one step.
The probability I'm reaching in one step. So x0 is like in 0 steps. So which is like, I mean, right now everything is 0. And x1, what I'm doing is like, I'm adding the b. I'm adding the b. Okay, so I'm reaching in exactly one step. What is the probability in reaching it? So that is my x1. Okay, so for because I'm talking about the S question states here. Okay, so I'm not talking about the states which are already in T, but the states which are not in T, so they're in S question. So now I'm saying that what is the probability that I'm reaching T in exactly one step. Okay, now when I'm talking about x2, right, what do I have? So I'm talking about like, and x2 is, remember that it is like the ay plus b.
So the A
So ay gives you like in two steps, and then I'm having the plus b, which gives me also in one step. So this is the 2 when I'm having the x2, this is like in one step as well as in two steps. So which is like in at most two steps. When I have x3, then I have the x2. I have the x2 which was with 1 and 2 steps, right? And then I'm multiplying with the a again. So that gives me in 2 steps and 3 steps, but I'm adding the b again. So that gives me in 1, 2, 3 steps, at most 3 steps, right? Now x4. X4 had already 1, 2, 3, and you multiply the a, you get in 2, 3, 4 steps. What is the probability? Plus b, also include the 1. So you get in 1, 2, 3, 4 steps, right? So it's immediately, it's not clear why it should be like in less than equal to n and not equal to n. But you have to, if you think a bit, you will be able to figure out that like it's actually less than equal to n steps you are reaching the target. Clear? Good. Right? Because otherwise you may not have these things. So maybe sometimes I may reach somewhere in 2 steps. This will not be monotonic like this. If I have that I'm reaching somewhere in 2 steps, I'm reaching somewhere in 3 steps. Maybe the probability in reaching somewhere in 3 steps will be smaller than reaching somewhere in 2 steps, right? But if you sort of have this, like because of the B, like you are including everything in at most 3 steps, in at most 4 steps, of course, this will be monotonic. Okay. So you can ask such questions then, what is the probability that it will be eventually delivered, right? So it will be like limit n tends to infinity xn. Then what is the probability that the message is delivered in at most 3 steps? Something like that. You can ask such questions, right? And this will be like you just start with that 0 and then multiply, right? You will get this information, like in at most these many steps, right? So if you solve the LP, you don't get that these information, like the intermediate, like in so many in n steps, what is the probability of reaching? That you don't, you won't get. But if you do this iterative computation, you will also have additionally like this information corresponding to every n, right? And sometimes it turns out that these iterative computations are faster if you have a large Markov chain and things like that. It may turn out to be faster at times. Okay. Yeah, but not always necessary. But yeah. So let's just look at this example. So this is an example of, I think it will be clearer even, iterative computation of, like, I just want to make sure that we understand well. So here is an example. And so what I want to do is, like, when I write F2, so it means that in at most 2 steps. Okay. So can you just compute this? Like, so what I want to do is like from state S0, I would like to reach S2 in 2 steps. So you start with, of course, like you can see this and get this very easily, right? Like, so you have like this, so this is in 2 steps as well as this is in at most 2 steps, right? So 1/6 plus 2/3, you get some number. But I want you to do this with this iterative computation, like you set 0, multiply with the A, and then add the B. Can you do this and tell me what like you get? Right? Mhm. So my S question I'll start with like S0 and S1. Okay. And then I have to set up my equation, this A and the B. Okay. And then I'm trying to compute this x's, right? So initially I have, so initially I can have the x's 0, x's 1, and then the 0. It's like this. And then this is like A times the A times initially, like, sorry. So if I say 1, 1, this is like x's 0, x's 1, then the 0 plus this b. Now this, to start with, this vector is 0. To start with, this vector is essentially the 0 vector. So I have this. And then I should also see what the b is and so on. Okay, so can you now try? So all I want to say is that in within at most 2 steps, so that means I need to find xs0, xs1, 2, which is equal to a times xs0, xs1, 1 plus b. So this is what we want. Clear? Yeah. So now you can tell me what value you get.
Second issue.
Yeah. So Vishal, are you able to follow?
Yeah. Some things maybe not, but this I can understand. Like I'll go through and look at the past lectures notes
Yeah.
again.
Yeah.
Yeah. To be clear, it's just the transition matrix, right? A is just the transition.
Indeed. A is the transition matrix which involves that S0 and S1.
Makes sense.
So yeah, can you tell me like what is the A matrix and what is the B?
Yeah.
So A is 0,
1/3,
1/3,
1/2,
1/2,
0,
0. What is B?
2/3, and 1/2.
2/3 and 1/2. Okay, good.
I got the other way around. I got 0, 1/3.
Because you put S XS3 in a different way, like so what is this?
So the probability we reach
So it's
is
like
1 from S0.
that is XS0 is the probability with which we reach S2, let's say, and XS1 is the probability with which we reach S2 from S1, right? So XS 0 equal to 1/3 XS1, right?
Access.
So this is the probability to reach S2, and XS1 is the probability to reach from S1 to S2.
But I did the probability to reach S1 from S0, not the to eventually reach. So I think I got the other way around.
So sorry. So okay. So XS1 is the probability to reach S2 from S1, right? And now I say if XS0 is the probability to reach S2 from XS0, right? So how am I getting this? My XS0 is like with 1/3 probability I'm reaching here, and then it is with the probability of XS1 plus with probability 2/3 I reach S2, and XS1 similarly is half probability I reach that S0, and from S0 I can, it's like that probability of reaching S2. So and with probability half I'm reaching S0, and then another half probability I directly reach it S2. Clear?
Yeah.
So then I get, if you now sort of try to write this down, you get exactly this, like XS0. So I say XS0, XS1, right? So this is equal to 0, 1/3, half, 0, XS0, XS1 plus 2/3 and half, right? So see, XS0 is 1/3 XS1, XS1, right? Plus 2/3. That is XS0. XS1 is half X S0 plus half, right? So this is the matrix. I mean, this is the linear recurrence, the linear equations that we set up. So now you have to compute that. Have you got it?
Yeah.
So what is your xs1? xs0, xs1. So what is this value?
XS1 is 1 by 9. 2 by 3.
2 by 3?
1 by 3.
Are you sure?
It will just be the B, right? So B is 2 by 3 and half. Half, not 1 by 3. Oh, that's very easy. Okay, I think that's why the looking.
Okay, and what is xs2 now?
5 by 6 and 2 by 3.
5 by 6 and 2 by 3.
2 by 3. 1 half plus 1. 5 by 6.
So that 5 by 6, 5 by 6, right? So this is xs2, what you get is 5 by 6, 5 by 6. Clear? Okay. Right? So this is how you compute. You start with 0, then you iteratively do 1 step, 2 step, and then you see that this value indeed, like what you get, it's correct. Like, so within 2 steps you want to reach here. From S1, with probability half you are reaching in 1 step, and in 2 steps you have half times 2 by 3. And this is exactly what you did, right? Half times 2 by 3 plus half. This is how you got it. When you are computing this is exactly what you did. Half times 2 by 3, half times 2 by 3. This is what you did, right?
Yeah.
Because you got a 2 by 3 here in xs1, this thing. And now you multiplied with half. Half times 2 by 3 plus half, right? And it's 5 by 6. And similarly from s0 also 5 by 6. Clear? So when you are doing this thing, this thing, this is like in at most 2 steps. It's not exactly 2 steps, but in at most 2 steps. You are reaching. Clear? Okay. And if you just want to compute this for C until T, here also we'll see that C until like in at most n steps here, the xn. We were just doing the eventually, but you can do it for the until also. That's all I'm saying. Okay. Right. Okay. Now, what we will do now is the uh, limit behavior of Markov chain. So what is the limit behavior? Like it's essentially about those BSCCs. So infinitely often what you'd usually see. Okay, infinitely often what you would like to see. So for example, in the limit, a run would like to see some set of states with some probability, right? So or with probability 1. So that is like the set of states in the BSCC. So just to say, what is a BSCC? It's a bottom strongly connected component. Bottom strongly connected component T, which is a subset of S, such that for all S belonging to T, we have that post of S is a subset of T. So there is no probability leak which is happening outside. Okay. Yeah. So, and this is one thing. So if you have this Markov chain, then with probability 1, the set of states which are visited infinitely often, this forms a BSCC. With probability 1, the set of states which are visited infinitely often is a BSCC. Okay, is it clear? Like if you may have multiple BSCCs, But with probability 1, you will end up in one of the BSCCs. Okay, will be like, so there can be other paths which don't form the BSCC. Like for example, here, let's say there is a path which is, sorry, there is a path here which is of this form, right? It's not a BSCC. Now, this is also an infinite path, right? But what is the probability of such a path happening is like it's zero, right? So with probability 1, a path will eventually end up here and just stay. So these are the BSCCs in this particular Markov chain. So the BSCCs, only BSCCs are these ones, right? And with probability 1, a path will end up in one of the BSCCs. Okay, so this is what it says. And so the set of states which are visiting infinitely often, this is in fact some BSCC, and that happens like with probability 1. With probability 1, that a path pi visits infinitely often all the states of a BSCC. That's what is happening with probability 1, right? This is what it says. That the set of paths such that the set of states that are being visited by the path infinitely often, so that is a BSCC, and this the probability of such set of paths is in fact 1. So with probability 1, a path pi will end up in some BSCC and visit all the states of that BSCC. Clear? Right. Okay. And once we enter a BSCC, we are always once we enter a BSCC, we are always inside the BSCC. We are always inside it. Clear? And a BSCC is also something where it's first of all strongly connected, right? It's strongly connected. It's strongly connected, and there is also one more thing. So this is one thing. Then the other thing is such that no superset is strongly connected. Okay. Okay. So usually this largest strongly connected set, the maximal such strongly connected set, we call them like is the strongly connected component. So this is a strongly connected component. A strongly connected component is one which is a maximal strongly connected set. Okay. Connected set. This is my SCC. Clear? Okay. Good. So now I think, okay. So if I now have to talk about like say we are talking about some behavior in the long run, right? So for example, infinitely often something is going to happen, or like let's say which is something like um, a prefix independent property. So something, it doesn't depend on the initial prefix of the run, right? So eventually something is going to happen. And if we want to talk about the measure of such events, such events, then we are going to focus our attention only on the BSC. So we can restrict ourselves only on the restrict ourselves only to the BSCs of the Markov chain. Okay, so for example, let's say if I talk about this infinitely often, I would like to see the set T. I would like to see some set T. Okay. Now T is some subset of S. Infinitely often, I would like to see some subset T of S. And I'm trying to see what is the probability of this event. What is the probability of this event, right? So starting from state A, what is the probability of satisfying infinitely often I visit T? So how am I going to solve this? How am I going to solve this? Given some set T, it's not that like all the states of T have to be inside a BSC. So T is some subset of capital H, right? Now I'm saying that what is the probability of visiting the states in T infinitely often? How am I going to compute this, right? So here is something I have written like, so it's like I want to see, it is the same as probability of eventually reaching some U. What is this U?
The strongly connected component which contains T.
The strongly connected components
which have some intersection.
Which have some intersection with T. Very good. Okay. So strongly connected because the states which are outside the bottom strongly connected components, these are the bottom strongly connected components which have some intersection with T. Okay. There may be some states of T which are outside any of the bottom strongly connected component. But there may be some path which will visit those states infinitely often. That can happen. But what we have seen that anything outside this bottom strongly connected component, the probability of seeing those infinitely often or infinitely many times is zero. There can be a path, but the measure of that path is zero, right? So they don't contribute to the probability of satisfying this event at all because the probability is zero of satisfying those states which are outside the BSCs, right? So what is the U here? The U here is the union of, so this is a U, this is a union, okay? I'm sorry for the notation, but of the set of BSCs such that B belongs to BSCC of M and B intersection T is not empty. Clear? So the other states which are in T that are outside some BSCC doesn't really matter because you can only visit them infinitely often with probability Z. What about this? Like eventually globally T. Eventually, I'm going to see only states from T.
So you want the BSCC to be exactly T. T should be a union of some BSCs.
T should be a union of some BSCs. What does that mean?
In the sense,
so again, the T again T can be somewhere which is outside the BSCs, right? So that is possible.
Yeah.
And T can be some states in some BSCs. T can be outside BSCC also.
So if T is there in a BSCC, then no state which is not in T is in the same BSCC.
Right.
Okay. So T is the union of some BSCs and some things outside the BSC.
T can be the union of some BSCs and something outside. Okay. So T, yeah, you are right. Okay.
Those won't yeah.
So you are saying like this, and B is a subset of T.
Yeah.
Okay. B is a subset. So what is the idea? Like you reach some BSCC like this, and in this BSCC, you are saying that all the states of this BSCC, they are also all in T. Right? They're also all in T.
Yeah.
Right? Because if there is a state in the BSCC which is not in T, right? Then you will also be visiting that infinitely often with probability 1. Infinitely often you will be visiting that with probability 1. Right? So you are not going to satisfy that if infinitely often globally T, always T. Because you are going to see that infinitely often. It's not always the case that you will be in T. Right? So all the states in that BSCC have to be inside T, right? So that's the thing. Okay, good. So now let's try to see again an example. So suppose I have this T which is of the form S1 S4, right? Now I want to see globally eventuality infinitely often, right? Infinitely often. By the way, this is called like this infinitely often, or it's called repeated reachability. This is also called repeated reachability, right? You can see repeatedly I'm reaching. Repeated reachability. And this is like the Kobushi kind of a thing, Kobushi property, the persistence, right?
Persistence is good.
Persistence is, sorry, yeah, I mean, that's what I meant. Like this is like the persistence is like the FGT. Eventually, we're going and staying there. This is like a Kobushi property, and this is like a Bushi property, right? So FGT, it's also called a persistence property. You go and stay somewhere. If you're just talking about globality, then what is that property? Always in T. If I just say always T, it's called a safety property. Because you are saying I'm always inside T. Going outside T is unsafe. Globality is like a safety property. FGT eventually globally is like initially I can be outside, but finally I'm going there. So it's like a Kobushi or called a persistence. Infinitely often is like a Bushi property, repeated reachability. And eventually T, like somewhere you are going to reach something good is going to happen. So this is also called a liveness property. Like liveness is something should happen. Like yeah, like you leave and something good should happen sometimes. Okay. Right. So now let's look at this example. Like so you have S3, S4, right? Sorry. Okay, so you have in fact T is sorry, I said S1 and S4 is your T, and I'm going to talk about globally eventually T. So infinitely often I would like to visit these states S1s. So how do I compute this? Infinitely often S1, S4. How do I find this?
So we need to find the bottom strongly connected components which have S1 or S4.
Correct.
And we don't have it with S1 because if we have to include S1, we have to include one. Right.
Right. So because S1 there is no bottom strongly connected component because there's a probability leak. So what are the bottom strongly connected components? This is a bottom strongly connected component. This is another bottom strongly connected component. So now only I can see S4 belongs to this. Right. So I can, if I come here, once I'm here, then I'll be visiting S4 infinitely often with probability 1. I'll be seeing S4 infinitely often with probability 1. Right? So then all I need to see is that with what probability I will reach from S0 to this particular BSCC. That is all. Yeah. So this is like reaching. What is the probability of reaching the relevant BSCC, the good BSCC? Here there is only one good BSCC. Right? So what is the probability of reaching this? Because once you reach there, then with probability 1, you are going to satisfy that always infinitely often visiting S4. Right? So now you can compute this, right? What is the probability of reaching the state S2, essentially, starting from S0. Clear? You can compute that using your standard linear equation. Yeah. So, right? Okay, good. Is it clear? So I'm not going through the computation. I think it's fine. When we talk about the limit behavior, there is also another thing which is called a steady state distribution of a Markov chain. Okay, so what is the steady state of a steady state distribution of a Markov chain? It's like if you run the Markov chain for a long enough time. So if you have, for example, a path which is there, then in the long run behavior, it says for how much time I'm in each of the states, right? So what is the frequency that I will be in this state, this state, this state, this state, and so on in the long run? Is it clear? So suppose I may be 20% of the time in this state, 30% of the time in this state, 15% here and 35% here. Just as an example, I'm saying it. They may not be true even for this Markov chain. I have not computed. But all I'm saying that this is the meaning of the steady state distribution. That when the Markov chain, there's a path, there's an infinite path of the Markov chain, which you can think of this as like the system is running for a long time. Then eventually in the limit, for how much time the path will be spending like in each of the states, what fraction of time the path will be spending in each of the states. Is it clear? So that is the notion of steady state behavior or the limit behavior, right? So if I talk about this distribution, right? It's a distribution. I'm talking about how much fraction it's going to stay in each of the states. So it's going to stay in some P1, suppose some fraction, suppose I call this maybe, let's say, Vs corresponding to start, Vt for try, Vd, Vl, like this, okay? Now, all I'm saying is that now if I sort of multiply this with the transition matrix, which I call P, then I'm going to get the same vector. Clear? Because if it is steady state, then all this transition, this transition sequence is not going to change the distribution further. Okay, it's in a steady state like what's Vt, Vd, Vl, right? So now that is the thing. Now, if you talk about the steady state behavior, like, I mean, I also have this kind of a thing, right? Like, so for whatever fraction, let's say I'm going to, so how are you going to write the corresponding equations, right? How am I going to get this thing is essentially I can see that like, okay, I can write the P, okay? So can you tell me what the P will be? I mean, you can get it from here directly. So one thing is like, if I have to compute this, so Vs plus Vt plus V, okay, so I just wrote them in slightly different order, so I'll follow that. Yeah, it doesn't really matter. Just VL and then VD. Okay, so yeah, okay. So okay, and so these are the things that I have: VS, VT, VL plus VD equal to 1. Okay, right. So this is the thing. So I have the V is the distribution, like the distribution in the sense that with what fraction I'm staying in each of them, and then summation V is 1, and then V times P should be V. Okay, so if I try to see how the P looks like, so I can say that VD is the same as VS. Is this clear? So I'm just trying to find my transition probabilities. Like I'm just trying to write the P, that's all. So the Markov chain is already given. So I'm just trying to write the P. And in order to write the P, I'm just writing these things. Okay, from this you can write the P in a matrix form. But I just find it easier to write it in this way. So VD equal to VS. Can you tell me the other things? Why VD equal to VS? Because if I'm here 20% of the time, then I'll also go there with probability 1. So I'll be here 20% of the time as well. So this is this, right?
VL plus VD is VT.
VL plus
VD equals VT. No.
No.
VL plus VS equals VT.
Yeah. VL, VS plus VL equal to VT. Because if I'm at the start, then I'll come here. If I'm lost, then also I'll come to try. So whatever fraction I'm here and whatever fraction of time I'm here, their sum will give me the fraction of time I'm here. Okay, then what?
VL.
I will say 1 by 10 VT
equals
VL. And what else? 9 by 10 VT equals VD.
Yeah.
Okay. So, right. So let me try to write down now the P here. So we have all these, right? So okay. So can I now write the P? So I have VS, VT, VL, VD. And on just writing this, you can figure out, you can verify. Yeah, maybe then you can tell me what shall I get. So what is this mean? Like this is yes, I think we should write it. Yeah. So I'm saying that this like Vs times. So suppose I'm going to compute, let's say the VL. So VL equal to 1 by 10 VL equal to 1 by 10 of VT, right? So here I will say 1 by 10 then. And then VD equal to 9 by 10 VT. Okay. Okay. So this gives me VS, because I'm writing this, right? VB equal to V. VS VT, VL VD. Okay. So is it clear like how I got this matrix? Right? This is just essentially you're writing all these things, that equations that we have in the blue. So this gives us this matrix. Maybe I should color this in blue. Clear? And now if you solve them, you could have directly solved them using all these things we have, right? So what do you get for VS? Can you tell me? You don't even need to look at, you can just look at these things and you can tell me what you get for VS. Right? So VS will give you that for what percentage of the time I am in the start state. That is VS. Similarly, I can talk about V try, I can talk about V now. Yeah, I'm just asking you to do these things because we are not going to have another homework assignment where you will get to do this. It's not very difficult. It just requires a little bit of familiarity so that like this is how you write the excess and all. It's not too difficult, but just sort of being slightly used to. 9 by 29. Good. Okay, so I also got this 9 by 29. This is DS. Okay, you can compute and get it. Good. Okay, so this is called the steady state behavior, steady state distribution. This V that we got, it's the steady state distribution in the Markov chain. Okay. So when we talk about the limit behavior, like these two things are important. One is the steady state distribution. The other thing is like you have to talk about the BSCCs, to which are the important components. Okay. Any question? No? Okay. So if no, then we'll move to the next topic, which is called probabilistic CTL, which is the logic, right? Now we are going to talk about some properties. So what do you do in model checking? You are given a property, you are given a model, and you verify whether the model satisfies the property. So now the property is given in the logic PCTL, probabilistic CTL. And what is your model?
The probabilistic, not automata. The Markov.
The Markov chain, right? So your model is the Markov chain. Your model is the Markov chain, and you have a formula which is in PCTL, right? So now you want to check whether the Markov chain satisfies this PCTL property. So you have this kind of, so everything you see, it's very similar to CTL. In CTL, okay, if you look at this for a while, so what difference you find with respect to CTL? What difference do you find with respect to CTL? What is there in CTL which is not here? What is
just the probability thing?
The probability thing,
yes. Until
within L steps is there, probability thing. And what is not here?
Globally.
Globally, you can get using the until, the eventually globally. You also have the negation here, right? Right. Yeah, right. So we are talking about this positive normal form. I'm giving you both conjunction and disjunction. So the negation is in the on the just on the propositions directly, but that you can also write. I mean, it's equivalent to like we have seen the standard thing where even if it is not in the positive normal form, but what is there in CTL which is not here?
Next is also.
Next is also there.
Is there like this true formula?
So true, false, you can say, but it's pretty much, I mean, you can say like I have the true and negation.
So these are there by default. True and
these are usually there by default, so we often don't say them, but yeah. What is there in CTL? What is an important thing we have seen in CTL?
state formula.
State formula, path formula here. Also, it's like, okay, it's similar to that. I'll come to that maybe. But just by looking at the syntax, don't you see something missing here, which is there in CTL? What was there in, what are the things, if you recall CTL, what was the syntax, what you had there?
Oh, we don't have quantification.
We don't have the quantification over the paths, right? Like you had for all paths, there exists a path, and so on, right? You don't see that. But instead, what you see is, so here for all, then you had a path formula psi, right? For all, and then there was a path formula. For all paths, let's say you had phi 1 until phi 2. For all path, or there exists a path, you had like eventually phi, like this, right? And these are state formulas, right? These were state formulas in CTL. They are alternating, right? So this is a state formula. This is a path formula. You fix a path, like for every path, once you fix a path, in that you have this as a path formula. There is an until, and these are again state formulas like that, right? Here, now instead of those, you have a probability of satisfaction of that path formula. Probability of satisfying that path formula. Clear? So I'm not saying that for all paths there exists a path. For all paths, this path formula, instead I'm saying the probability of satisfying this path formula is something like C. And this is like either strictly greater than or greater than equal to. Clear? So this is the main difference. And then you have exactly the same thing. So these are all state formulas. The psi is a path formula. So in psi you have the path formula, right? And now I'm talking about instead of for all paths exists a path, the probability of satisfying the measure of with which I will the measure of this path formula that is being satisfied from this state, right? Over what is the probability that all the different paths that are going from this state, with what probability a path is going to satisfy the formula? Okay, what is the measure of the set of paths which satisfy this formula? Okay, or what is the probability that a random path that starts from this state satisfies the formula, satisfies the path formula, right? So this is what we are talking about.
So for all will be like probability 1 and there exists like probability not 0.
Probability greater than 0. That is the kind of thing. But we have already seen, if you recall, that they're not exactly the same. That's the intuitively, that's how it should be. But we'll see again like they may not be the same. Right? So, well, let's now look at the syntax again. So you have also this bounded until property. It's called a bounded until. Bounded until. What is this UL? What is this UL?
That the C phi1 until phi2 and the phi2 comes within L steps.
Within L steps, right? So, I mean, my notation will be slightly confusing, but when I say L, L, then it's like within L steps. Clear? Within L steps. Okay. If I have to write exactly L, I will write it like this, equal to L. Like I'll say F equal to L. That means with exactly L steps. Okay. So now I will say that phi1 until L phi2, it's like the following. So you have this, and then you say, like, suppose this is your L. So somewhere before the L steps, phi2 has to hold true, and everywhere before that, phi1 has to hold true. But the phi2 has to hold within L steps. Clear? So this is the. And now sometimes I will also use the notation Pj of psi. Instead of saying P of psi is like greater than equal to C, I can also say Pj of psi where J is an interval. So it means that the probability of the set of paths which satisfy the formula psi, that is in the interval J. That is in the J is an interval. That is in the interval J. Okay, so that's just it's just another notation, but it's not nothing like it doesn't make the logic any more expressive or anything. I mean, it's just another way of writing. Like whenever I find, I just sort of like use whatever notation which I feel like often. So instead of sometimes writing like this, I mean, okay, is it clear? And this is clear, right? What it means. Like essentially the meaning is this. That starting from some, if I'm talking about whether a state S satisfies this, whether a state S satisfies this, it means that starting from S, you look at all the paths which satisfy the path formula psi, and then the measure of this set of paths should be in J, or the probability that some path satisfies this in J. Right. So I think this is something we understand. Like it's just like CTL, the PCTL semantics is just like CTL. So we can skip this. It's fine, right? And so let's look at the semantics. The semantics is with respect to Markov chain. Okay, the semantics with respect to a Markov chain. So for example, the CTL semantics was on a Kripke structure, on a standard transition system. Here, the PCTL semantics will be with respect to a Markov chain. So for example, suppose I say that probability of A until 3B, Okay, if b greater than equal to 0.5, and I'm checking this from the initial state case unit. So I already write here it doesn't hold. Why it doesn't hold? Can you explain?
So if we go at the left side, that means immediately see a B.
Correct.
So that probability is 0.1.
Right.
Thus, if we go to the right, we are not seeing a B immediately.
Yes.
Then if we go down, it's not satisfied, so we have to go here. Yeah, just enumerate all possible.
Correct. Right. So this probability is like 0.6 into 0.8 into 0.8 again, plus 0.4. It'll come to, I think, 0.78 or something. So it's not greater than equal to, right? And in 3 steps, right? So the other paths, they don't satisfy, right? Because you have a negation of A, negation of B is what is happening. Good. Okay. Now, what about, look at this formula, which is slightly more complex. Probability of some path formula.
Next one is like.
Next one is same as next.
Okay.
Next one is same as next. Okay. Now, what does it say? That in the next state, you are going to satisfy, so the probability that some successor of state init will satisfy this, some successor. So you look at all the successors. Sorry, you look at all the successors. Now you see that they have to satisfy this formula A, and within 2 steps, B has to be seen with probability greater than 0.4. So now this one doesn't satisfy this because A is not there. This one satisfies this. Now, what is the probability? Like it satisfies this, and does it satisfy this? Like with probability 0.4 greater than 0.4 greater than equal to 0.4, can I see B in 2 steps? So I have to see B in 2 steps. I can see B in 2 steps here. So this is indeed with probability 0.8 times 0.8, which is 0.64, which is greater than 0.4. So this successor indeed satisfies this part. So what is the probability of finding such a successor? It is 0.6 exactly, which is less than equal to 0.6. Hence case it satisfies this entire formula. Okay, right? So you can have nested probability operators, right? It's just allowed by the probabilistic CTL, PCTL formula. You have nesting in the path operator. Inside the path, you do x of phi. Phi becomes a state formula. In that phi, you can again have a probability p. Right? So this is how it's works. So now the question is that, okay, just some small syntactic sugar, which is like if you talk about probability of globally phi less than equal to p, it is the same as that if you suppose if S satisfies this, right, that you are satisfying globally phi with a probability less than equal to p, then you will satisfy eventually not phi with a probability greater than equal to 1 minus p. Clear? Always phi with probability less than equal to p, then eventually not phi, which is just the negation of that formula, with probability greater than equal to 1 minus p. Okay, now here is just a small thing. If I have to just, how do you write just some examples of some formulas, that all numbers have probability 1 by 6 to each, all these numbers. Okay, so you can say that, see, remember that the conjunction is on the state formulas. You don't allow conjunction on the paths, right? This is a state formula, that probability f of I is 1 by 6, and there is a conjunction over all the i's, right? So this is an example of a PCTL formula. And indeed, you can check this. For every individual I, you check whether this holds, and then it also holds for the conjunction. Now, how do you solve? Okay, I'll take maybe another 2-3 minutes and I'll finish. And then we'll come back to this. So what I wanted to do at the end is some comparison between PCTL and CTL, and essentially try to prove that, to show some proofs like that they are not equivalent. So what is the notion of an equivalence? That also one needs to define. When you say a PCTL formula and a CTL formula are equivalent, because their syntax are different. CTL is evaluated on a standard Kripke structure. PCTL is evaluated on a Markov chain, right? Then when you say that a PCTL formula and a CTL formula are equivalent, what does it mean? I mean, we should define the notion of an equivalence, and then we should say something like CTL and PCTL are not equivalent, right? So that, huh?
Are they comparable?
They are not comparable. They are not comparable, right? So I will show something in the next class, and maybe I'll try to show some proof. Usually, whenever you talk about two logics being not equivalent and they are incomparable, so these are usually difficult questions, okay? Like two things are not equivalent. You have to find some example, either some way, some counter example, something, and these are usually difficult questions. So I'll try to show something, one such possible proof for some examples, like for example, given a particular PCTL formula, you'd like to show that there doesn't exist an equivalent CTL formula. Okay. And there is also the other way around also. There may be CTL formulas for which we don't have equivalent PCTL formulas, which I will skip. But maybe, I mean, yeah, we have to select certain things which we can do in the class. But I will also tell you like where you can go and see these things. Okay, so the way you usually solve the PCTL model checking problem is again just like CTL. You look at all the different sub formulas and you try to see the satisfaction sets, and then you build, like you remember that we had a parse tree for the formula, and then you compute, like if you have a conjunction, then you take the intersection of the sets and so on and so forth, right? Now you don't have an exists and a for all, but you have the probability measure, and we saw how to compute the measure of these different kinds of path formulas, right? It's the measure is on the path formulas. What are the different kinds of path formulas we have? Here we have the next, we have an until, and we have a bounded until, right? And the weak untils you can also derive from using the until globally, etc., right? So we have these three kinds of path formulas, and if for each of them we know how to compute their measures, then we are done. Then it is the remaining part is just like CTL, right? So it's like disjunction, conjunction, negation. We know all of them. Essentially, we would take the parse tree, look at the sub formulas. If I can compute the probability measure of these things, these path formulas, then you can build up using that structural induction, you can build up the whole thing, and you can find the satisfaction state of the entire formula. And then we check whether the initial state is in that satisfaction state of the whole formula, the big formula, the given formula or not. That is the idea, right? And in order to compute the probability, what else do we need? In order to compute whether something is in fact uh, uh, I mean, what the probability of the set of paths? What do we need for that?
Probability over each.
Sorry,
Probability over
each path, but we need some property there, right? Like, so they have to be measurable. The events have to be measurable. The path formulas have to be measurable. So this is something we need, right? So, so this is what we'll see. In fact, like for each of these path operators, they are indeed measurable. Okay, because yeah, like measurable for every PCTL path formula psi, which the path formula may be X or unbounded until or until. For each of them, they are measurable. So this is what I have said, like this is a recursive computation, just like as we do for CTL, bottom-up traversal of the parse tree of phi. And this is the difference that we have. Difference with CTL is essentially these measures that we would like to compute, and the remaining is the same. And these are the different path formulas, and we can say that indeed they are measurable, so which we'll see. So I would like to do do the remaining in the next, starting from the next class, that for such path formulas, how do you compute their probability or the measure for these as well as for the until. And then I will do that difference with CTL. Like indeed, there are formulas which are in PCTL, no equivalent formula exists in CTL, and vice versa. So I'll not go through all the proofs, but maybe I'll give some examples and pointing to the places where you can find the remaining details. And maybe I will talk a little bit about weighted Markov chains when you have weights on the edges, and they sort of model some quantitative properties. So, for example, you can talk about some time required to do a task or some power that is used on a particular some model and things like that. Okay, or some payoff that you can get at the end of a computation and these kind of things. So these are modeled by the weighted Markov chains. So I'll talk a little bit about those weighted Markov chains, and then we'll finish this probabilistic model checking part, and we'll start with the reactive synthesis. Okay, any question before we stop? If not, then let's stop the recording.